Today we have Haotian from University of Chicago talk about his recent work on the Beck-Fiala Conjecture.
Cool. All right, thanks for the introduction, and thank you for inviting me to give this talk here. I'm going to talk about some recent progress on the Beck-Fiala and Komlos conjectures. This talk will be based on joint work with Nikhil Bansal from the University of Michigan. So this is about combinatorial discrepancy, so let me define what this is. We are given a universe of n elements and subsets S1 to Sm. Our goal is to color these elements red or blue so that all the sets in the set system is as balanced as possible, okay? Meaning they have similar number of red and blue elements. More formally, given any n by n matrix A, right? A can be an arbitrary matrix, but if you want to capture that set system above, for example, you can take A as its incidence matrix. So this is a 0, 1 matrix whose rows are the sets and columns are the elements. And an entry is 1 if the element corresponding to its column is inside the set corresponding to its row, okay? And 0 otherwise. Okay? But generally, A can be anything, so it's more general than set systems. I define the discrepancy of A as the minimum of the L-infinity norm of A times X over all the plus minus 1 vectors X. Okay? And to see why this captures this intuition of balanced coloring above, think of this vector X as your coloring. And minus 1s are the red elements and 1s are the blue elements. Okay, now if you look at any entry of this matrix A times X, okay, any entry of this guy, that would correspond to some row here of this matrix A, the inner product of that row with the coloring X. And that is exactly the difference between the number of red and blue elements inside that set. Okay? So if you take the L-infinite norm, that's basically the worst imbalance of any set in your set system. So this is exactly capturing what is the this imbalanced, balanced kind of coloring notion above. All right. So I want to take an alternative view of this notion of discrepancy. So let's call the column vectors of A as v1 to vn. Okay? So the L-infinite norm of A times X, this is the same as L-infinite norm of sum of xi vi, right? So this gives you an alternative and actually equivalent view of discrepancy as a question of balancing vectors. So we are given these vectors v1 to vn. These are the columns of your input matrix A. Your goal is to find plus minus 1 signings so that the L-infinity norm of the sign sum is as small as possible. So this kind of question of trying to split a set of objects into two similar parts is, first of all, it's an interesting, nice combinatorial math questions. But also it has many, many applications, right? In computer science, for example, you have randomized controlled trials, statistics, sparsification, rounding, machine learning, complexity, privacy, quasi-Monte Carlo, many others. I won't dive into applications in this talk, but here are some standard textbooks if you're interested in finding out. Okay, one thing I want to mention, though, is that for all these problems, you can always choose your signing X or coloring X uniformly at random. Pick a uniformly random plus minus 1 coloring, but this ignores any structures in your problem, right? So discrepancy theory is all about beating random. Okay? And in many cases, you can actually do much, much better than random, and even without structures. So let me explain what this means without structures. So here's one example. It's a standard problem called Spencer's problem. In this problem, we are back to the set system. We have n sets and n elements. So A is a square matrix. 0, 1 square matrix, so m equal to n. In this case, if you do random coloring, the discrepancy is typically square root of n times square root of log n. Throughout the talk, I'm going to ignore constants. Sometimes don't even explicitly write it out. So this is a very simple proof. Why? Because if you do random coloring, uniformly random coloring, every set will have standard deviation square root of n. At most square root of n, but sets can be long, so typically constant times square root of n. But they also have a Gaussian tail because of concentration, right? Standard concentration inequality. So the probability that each set has discrepancy c times square root of n is at most exponential of minus c squared. Now you can take c to be a constant times square root of log n, and this allows you to do a union bound over all the sets. Okay? Actually, with high probability, square root of n log n. Okay. So generally, if you do random coloring, this square root of log n is needed. It's necessary. Okay. But surprisingly, Spencer showed that you can actually avoid this square root of log n coming from this union bound and find some coloring x with discrepancy only a constant times square root of n. Okay? This is very surprising because a priori, there's no reason that this is even possible. It turns out that only exponentially small fraction of the colorings can achieve this. So this is not typical behavior. This is an extremal behavior. Okay? The proof of Spencer's result, I won't go into much depth in this, but it uses a standard method now called a partial coloring method. This was originally studied by Beck and strengthened by Spencer using a sort of combination of entropy and pigeonhole principle. Alternatively, in 2 years later, Gluskin found an alternative convex geometric approach of partial coloring method. Okay, so Spencer's problem basically assumes nothing about the matrix, just that it's a square matrix, right? So basically no structure. But when you do have structure, you can often do much, much better. And here's a very classical problem called the Beck-Fiala problem. And here we are assuming that, okay, a set system, but each element now only lies in a small number of sets. Or in other words, the A is a m by n matrix, which is k column sparse. Okay, or if you're happy to think about hypergraphs, this saying the degree of every element is at most k. Okay, one thing here is that this k is really the parameter that we really care about, right? We usually think of k to be much, much smaller. M and n is not that important here, so we can pretend that they're the same using some standard reductions. I will get back to this point briefly later on, but for now, just don't care about m and n. Okay, so this is a generalization of Spencer setting by basically putting k equal to n, you get Spencer. So again, if you do random coloring, discrepancy is pretty large, at least square root of n, right? If you have, as long as you have any one large row containing of a linear number of elements, that guy has discrepancy square root of n. Okay? But it turns out that you can do much better. So in fact, Beck-Fiala showed in 1981 that you can get a discrepancy that's linear in k using linear algebraic arguments. And they conjecture that the correct answer should in fact be square root of k. And note that this will, if this conjecture is true, this will nicely generalize Spencer's result to all k. Okay? So, but this is a much harder problem. And in fact, Spencer used the same partial coloring method and can achieve a square root of k times a log n bound. And this was later improved by Banaszczyk in 1998 to square root of k times square root of log n using deep ideas from convex geometry. Okay, so in particular, one thing I should note is that the best bound for the Beck-Fiala conjecture previously is formed by a combination of Beck-Fiala's linear in k and Banaszczyk's square root of k times square root of log n, depending on how large k is. In particular, these two bounds meet at k equal to log n, where both of these bounds are log n. And this is the part of kind of the regime that will really, kind of talk a little bit more in depth. So keep that log n in mind. I will get back to that. Yeah, so far things are just existential. Yeah, that's yeah. Algorithm part will be a very important aspect of this talk. Okay, I want to now generalize the Beck-Fiala problem one step further. Okay, so you don't have to look at even a set system, right? Now, so in the Koml setting, we are given unit vectors v1 to vn, right? Euclidean norm at most 1. And equivalently, the input matrix A has unit length column, or at most unit length columns. So the Beck-Fiala problem is a special case of this problem for any k column sparse input matrix A, because every column now has Euclidean length square root of k. So if you scale down A by this 1 over square root of k factor, you will get a matrix whose columns are at most unit length, right? So so basically this says the Beck-Fiala is you can reduce to a Komlos instance. And in fact, Komlos conjecture generalized Beck-Fiala conjecture by saying that the discrepancy of unit vectors at most are constant. Right? And for this problem, the best bound is in the same paper by Banaszczyk, who proved a bound of square root of log n. And it has been the best bound since then. Okay? One thing I want to sort of mention is that there's no clear consensus on whether people actually believe in this conjecture. In fact, Haotian in 1988 conjectured that this later bound by Banaszczyk should be the correct answer and give actually some partial evidence of this. But despite a lot of effort, the current best lower bound is still a small constant, 2.4 something by Kuniski. I want to mention in passing that there are other recent surprises about some other constant discrepancy conjectures. For example, for Erdős discrepancy problem or Beck's free permutation conjecture, Tao and Newman-Nikolov showed surprising that these conjectures were actually incorrect. So what did we prove in our work? So we showed an improved bound for the Koml problem. So by giving some kind of positive, this gives some positive evidence that Koml might be correct. So we give this improved log into the 1/4 bound for Koml, where that O tilde hides polylog-log factors, which we will not really care throughout. And this is the kind of first improvement over Banaszczyk since 1998. And this is, for Beck-Fiala, this gives square root of k times log into the 1/4 for all k. Okay? But for Beck-Fiala problem, we could actually say something better for different regimes of k. In particular, we can prove the Beck-Fiala conjecture when k is at least log n squared. Previously, this conjecture was only proved in Spencer's result, basically corresponding to k equal to n. Okay. What about when k is really small? Okay. We can get some improvement of, so we can get an improved bound of square root of k plus square root of log n, again up to log n factors, and this replaces Banaszczyk, essentially replaces Banaszczyk square root of k times square root of log n by a sum. Okay. So it's some improvement, but as you see, like when k goes down, this square root of log n at some point will be the bottleneck. Okay? That happens exactly when k becomes smaller than log n, then there's no further improvement in this bound. And if one can further reduce this additive square root of log n, that might directly lead to an improved bound for the Koml problem. This additive square root of log n is really the bottleneck here. Okay, any questions so far before moving forward with result and setting? Okay, perfect. So one important aspect is that all our results are made efficient polynomial time algorithms. And not just so, they're actually crucially based on these algorithms. So let me talk about algorithmic aspect of discrepancies. Marsh mentioned earlier. The partial coloring method and Banaszczyk's method that I mentioned, these were originally existential. They proved that some coloring with very small discrepancy existed, but did not give any algorithm to efficiently, or in polynomial time, find one such coloring. Okay. But over the last 50 years or so, there have been a lot of developments in designing efficient algorithms for these discrepancy problems. And now we can sort of match the partial coloring method and Banaszczyk's approach almost in their full generality using an algorithm. And in fact, our results will be built on this, this first result here by Banzo, Dadush, and Garg in 2016, who gave the first algorithmic proof of Banaszczyk's square root of log n bound for the Koml problem. So here's the plan for the rest of the talk. As a warm-up, I want to sort of go over this Beck-Fiala algorithm that can get, the original paper by Beck-Fiala automatically also gave an algorithm. We're going to go over that algorithm that gives you a constant times k discrepancy, and also go over this BDG algorithm that gets square root of k times square root of log n for Beck-Fiala. We'll discuss why these algorithms are stuck here, and discuss some new ideas to give an improvement. And then I'm going to discuss a basic version of our method, which gives a square root of k times log into the 1/4 bound for Beck-Fiala. Okay? We're basically going to focus on this k equal to log n regime mentioned earlier and prove a log into the 3/4. We recall earlier bounds were log n, so this already gives a log into the 1/4 improvements over previous bounds. Okay, finally, I'm going to mention some extensions which gets the Koml bound and the stronger bounds for Beck-Fiala. Okay, cool. Let's recall the Beck-Fiala setting. We are given as input a matrix A that is k-column sparse. Okay. As mentioned, I can assume M equal to n with a loss of generality. The sort of trivial way to do this is you pad the matrix A with zeros to make the dimensions match. This is not very efficient if the dimensions are very different to begin with. Okay? But in those cases, it turns out there's something smarter that you can do. I won't dive into these technical nuances. Yes? K-column sparse? You have k on your column, or each column is each column is k sparse. Yes. So each column has the most k1s, is what it means. Good question. Yeah. Okay. So for the rest of the talk, don't worry about m not equal to n. Okay? So what does column sparsity really buys us, right? Column sparsity implies some kind of row sparsity, but on average. In particular, because each column of A has at most k1s and there are n columns, right? A has the most n k1s. And like there are m equal to n rows. So this implies that the average row size is at most k, right? The rows are small, but there can be long ones, but not too many of them. It turns out the rows whose sizes are much larger than average, these are the problematic ones. The short rows are actually fine. So we'll call a row large if its size is more than 10K. And because the average size, row size is at most K, right, this implies that there can be at most n over 10 such large rows. Okay, so why did I say that large rows are problematic? If A had no large rows to begin with, then I claim that this Beck-Fiala result of constant times K or Banaszczyk square root of K square root of log n are kind of very easy to get. Why? Because any coloring would have discrepancy K, right? The rows don't have size more than 10K. Right? I'm skipping constants here. And if you do a random coloring, using the same kind of union bound, right, with the concentration, this gives a discrepancy of square root of K times square root of log n with high probability. So in other words, if A had no large rows, the results are really trivial. So the main idea of Beck and Fiala is that you can essentially pretend, although they are large rows to begin with, you can pretend that they don't exist by simply walking orthogonal them. I'll explain what this walk orthogonal means. But in the modern language of algorithm design, this is called iterated rounding. This has now become a very standard paradigm for designing certain kind of algorithms. Yeah. No, this is just a standard variable. Like each row has at most 10K elements, right? So you just use Haotian inequality. Yeah. Nothing here will be about matrix, matrix concentration. Yeah, just standard variable concentration. Okay, now let me tell you what it means by walking orthogonal. This is the crucial idea of Beck-Fiala. I'm going to describe Beck-Fiala algorithm in a slightly different form than what appeared in the original paper, but it's really an equivalent way. I just want to put everything in the same framework. So here's the algorithmic framework that we'll use throughout the talk. So how do we compute a coloring, right, by an algorithm? Well, let's think of this unit hypercube, -1, 1 to the n, and every vertex is a +-1 vector, right? I'm going to think of every vertex as a coloring. And I want to compute and coloring by starting from the origin and taking a random walk until I hit one of the vertices. And the one thing I want to one property I want to make sure is that whenever a variable becomes +-1, that variable will not be changed ever afterwards. Right? So in other words, geometrically, whenever you touch a facet, you're going to stay on that facet. Okay. It's you start from the interior, but then once you touch the surface, like once you touch a facet, you will stick on that facet. And when you touch another lower dimensional edge, you're going to stuck on that edge. Yeah, that's what that second thing means. Yeah, but you start from the interior. Yeah. So xt denotes the, let's fix some notation to talk about things. Xt is the fractional coloring at time t. Right? So, and it's going to be updated by a tiny centered Gaussian vector delta xt with covariance sigma t. So this is really, you can think of as a Brownian motion, but in a discrete way. Okay? That's how you get polynomial time algorithms. So the power of this framework comes from the ability to choose sigma t adaptively, right? If some set has large discrepancy, you might want to make sure you don't hurt that set anymore. You can adaptively choose where, depending on your history. So nt denotes the number of alive coordinates, meaning that they have not yet reached +-1. And that property above basically says only alive coordinates are going to get updated. Those touching +-1 will get fixed. Okay, last piece of notation, let A1 to AN denote the rows of the input matrix A. And let DTI denote the one-sided discrepancy. That's basically an inner product of the row I with the fractional coloring xt. It suffices to control one-sided discrepancy. You can append every row, the negation of every row, into the matrix. Of course, this creates -1 entries. Okay, but the algorithm can handle -1 entries, so that's not a problem. What is it?
The alive coordinates are always 0.
The alive coordinates. You don't have to, but you can think of this the change in delta xt as 0 on those coordinates. So you can think this inner product is on the yes, yeah. So right. So basically, you think of this as a tiny Gaussian update on the alive coordinates. Yeah. Right. Yes. Yeah. That's exactly correct. And this update is going to be the discrepancy of the ith row. One-side discrepancy is going to update it as AI inner product with delta xt. Okay. So here's the Beck-Fiala algorithm. Let's call a row large at time t if there are at least 10K alive elements in that row. And by the same averaging argument, right? Because looking at all the alive columns, there can be at most K in every alive column, NT alive, so it's K times NT once in the alive columns. By the same averaging, this means that at any time T, there can be at most NT over 10 large rows. Okay, so the algorithm is going to be basically, I choose my random walk to be orthogonal to these large rows, and that's it. More formally, let WT be the span of the large rows AI. The dimension of this subspace is NT over 10, right, by the observation above. And choose delta XT as any step in WT. We are going to say WT is blocked, right, just for convenience. So this is the algorithm. You're going to do this until you hit a vertex. Okay, so what's the analysis? Well, this is the picture proof of this algorithm. This is how much the discrepancy changes as a function of its row size over time, and because it's rows for a fixed row, and because the row size of every row decreases, right? The size means how many alive elements are there in the row. That thing decreases as elements get colored. So this is the way to look at this is from the right to the left. I'll basically show these pictures for every algorithm I mentioned. Right? So it's good to back. Okay, yeah, so in the beginning, the row might have large size, but you know that as long as size is larger than 10K, it's not going to incur any. Sorry. Thing doesn't stay here. Okay, so yeah, as long as size is larger than 10K, this row is not going to incur any discrepancy because we're walking orthogonal to large rows, right? Now, as the row is smaller than 10K, okay, you don't really care. They can incur at most 10K discrepancy trivially. So this proves you a 10K discrepancy bound by an algorithm. One thing I want to mention, but won't really be very careful about, is that this 10K can be actually Beck-Fiala showed 2K minus 1. Okay, so in a sense, you can make that K kind of like K plus 1 or something, and then you basically when the row becomes small, you can only at most flip colorings. That's 2 per coordinate. So yeah, but let's not care about constants. But there's some interesting research. I mean, it's an interesting research question to kind of the best bound I think is by Boris' book, who get 2K minus log star of K right now. So it's still it's still pretty hard generally how to get something that's only depending on K, even just improving the leading constant from 2 to something smaller. That's open. Yeah. Okay.
Log stars, the number of logs until you get.
Yeah. Yeah. Yes. Yeah. Something that's bigger than than a constant. Yeah. But that shows kind of very hard to improve that too. Right? Yeah. Okay. But that's a different kind of direction. So now let's talk about how you get the square root of K times square root of log n for Banaszczyk. Right? As I mentioned, if there are no large rows to begin with, doing a uniformly random coloring would already give you the square root of K times square root of log n, right? And as mentioned in Beck-Fiala, oh, sorry, I think I jumped in. So as mentioned in Beck-Fiala, you can pretend that large rows don't exist by walking orthogonal to them. So what if we just walk orthogonal to them and be sufficiently random, right? This seems to combine the best of both, right? So here's the proposed algorithm. Let delta xt of WT again be the span of the large rows, that's NT over 10 dimensions. I'm going to choose now a uniformly random step in WT perp, right? And because WT perp still has dimension 9 NT over 10, right? That's a very large subspace. So this should give you sufficient randomness. And here's my proposed analysis. While a row I is large, it incurs 0 discrepancy as in the Beck-Fiala algorithm. Once the row becomes small, right, size smaller than 10K, and because I'm doing a sufficiently random walk in the space, I should be able to get a similar kind of Gaussian behavior for their discrepancy, right? So I should be able to incur a square root of K times square root of log n discrepancy. Unfortunately, this analysis is not correct. The issue is that as you have this kind of constraints, once you walk in the subspace WT perp, that subspace will incur some dependencies between the coordinates. And here's an example of why this is fatal. So let's say WT perp enforces that your update of the first 0.1 NT coordinates are all the same. Okay. And now if you choose, and let's look at a set S, which is the first K elements. Let's say K is smaller than NT in the current step. Okay? So once you do your update and say you update your first coordinate by either plus epsilon or minus epsilon, the first k coordinates, they must all be updated by plus epsilon or all be updated by minus epsilon. So the change in the discrepancy in the current step is epsilon times k, which is very different from that epsilon times square root of k if you do independent ID updates, right, for different coordinates. And this loses another factor of square root of k, and this seems to be a fatal problem. Okay? But surprisingly, you can actually design a smarter update delta xt so that it looks random in every direction, despite that you're being on a subspace. Okay? And here, if it's random in every direction, kind of it's also random with respect to every row, so that every row discrepancy is also kind of looking random as you hoped, right? How do you get around this? How do you handle this example above? Well, you just set all the first 0.1 anti-coordinates to not update. You're going to keep them fixed, and as you get elements colored, some of these constraints will get lifted, right? Because some of the rows will become small, you no longer block them, and that's when you really start to update some of these coordinates. That's how you should be thinking about it. But of course, this is kind of, this is not general. How do you make this general? Okay. Oh, one thing I want to mention is that you only consume 0.1 NT degrees of freedom, and that's okay. You have 0.9 NT degrees of freedom. Okay. So this is perfectly fine. It won't hurt your randomness. But how do you do this in more generality? This is what is called this very nice property called spectral independence. So BDG showed the following. Suppose W is a subspace with dimension at most epsilon n, where epsilon think of as 0.1, some small constant. Right? You can find a subspace, you can find a random update, unit-centered update delta x, so that, first of all, it's orthogonal to W, as before, but also it satisfies this so-called spectral independence. What does this say? So covariance of delta x is PSD bounded by 1 over 1 minus epsilon times the diagonal of the covariance. Okay, let me try to decipher what this means. So the interpretation is that, so equivalently for any direction A, the expectation of the square of sum of AI delta xi, this is at most 1 over 1 minus epsilon times sum of AI squared times the expectation of delta xi squared. This is really equivalent to this for all A, if you have for all A there. Okay, but what this means? So the point here is that really you move the square from outside of the sum to inside the sum. If you replace this 1 over 1 minus epsilon by 1, and this less than or equal to by inequality, this is nothing but pairwise independent. So really you should be thinking of the spectral independence as saying the update delta x1 to delta xn are just almost pairwise dependent, up to this 1 over 1 minus epsilon, which we are always going to think as a constant. Okay, so up to a constant factor, it is pairwise independent. Uncorrelated, yeah, yes. Yeah. But that's, yeah, pairwise, yeah, it's the same thing. Yeah, for mean 0. Okay. Yeah, so you should really just think of this as almost pairwise, kind of uncorrelated-ish.
And an efficient way to find that update.
Good question. Yes, I'll be mentioning. Yeah, it will be here. Okay. Yes. So give a Gaussian, and one thing. So this is a much weaker kind of independence, right, than random coloring. Okay? But it turns out that this would already give you a Gaussian tail bound for the discrepancy of each row, as you would hope. Okay, and proof of this is using some kind of Friedman type inequality to use second moment conditions. I won't dive into that analysis. Okay, the efficient way to generate this delta x comes from the proof of this theorem. You basically write it as a semi-definite program, and you can show that such a coloring, actually such a covariance matrix exists using SDP duality. I won't really show, it's some complicated calculation, but you can prove that such a covariance matrix that you want existed, and you just do a random projection onto a Gaussian. And this is also giving you a way to efficiently sample such delta x. You solve the semi-definite program, get this covariance matrix, and do a random projection. That would be your, yeah. Okay. Any questions so far?
So you have this random walk. Eventually, you want to get to a plus minus 1, then fix it.
Yes.
Since you're taking epsilon time steps, how does the fixing work? When do you decide to fix it to a plus or minus 1?
Oh, you just basically random walk until you hit a boundary. Oh,
you're going to walk all the way there. You never
So there is a rounding. I'm skipping that rounding. So you basically can round whenever you're like 1/2n close to the boundary. Yeah, yeah. That you have to do something like that. Otherwise, right, you will go outside, right? That's the worry. Yes, yeah. So I'm skipping that kind of. I'm thinking really about epsilon. It's very, very tiny. Sorry, this epsilon is not the epsilon. Like the time step, the step size is very, very small. So yeah. But yeah, you need to do some rounding for the where you're very close. Okay, so here's the BDG algorithm. You just block large rows as in Beck-Fiala, but also you generate the spectrally independent delta xt by solving the semi-definite program orthogonal to WG. Okay?
For each time step.
For each time step, yeah, that's very important. Yes. Yes, right. Yeah. So this algorithm is polynomial time, but a big polynomial time. Yes. Yeah. Yeah, and it would be very actually, as you mentioned, I mean, like it would be very interesting if there are like faster algorithms, and we only know very few fast algorithms for discrepancy. Okay, so we're still in the polynomial time kind of regime for efficient algorithms. Okay, so here's the analysis. Now for any arbitrary, okay, and this is the picture again. For any row I, if the discrepancy is large, its discrepancy stays 0 while its size is large. When small, it starts to have this kind of random Gaussian behavior, right? But now its standard deviation is square root of k. So the probability that dti is at least theta times k square root of k is most exponential minus theta squared. This comes just because, as I mentioned earlier, you have constant spectral dependence for your update, and that generates a Gaussian tail for your discrepancy. Well, in fact, that generates Gaussian tail when you look at any direction. Okay? So once you set theta to be square root of constant times square root of log n as before, this gives a union. You can do union bound. This recovers Banaszczyk square root of k times square root of log n for the Beck-Fiala problem. Well, this is a slow algorithm, but this is actually the simplest proof of Banaszczyk's bound that I'm aware of. Okay, so the punchline here is you can really walk in a subspace and still look sufficiently random. Okay, any question about this so far? This is really the state of the art.
Maybe not super well. Just computationally, have people experimented with bigger step sizes? Does it still work?
I think some people did, but you know, solving STB itself is a very painful job, right? So yeah. Yeah. I think some people did that. There's some work like that, but I don't remember what, you know, I haven't looked into that.
Still seems to empirically work or not.
Yeah, there are some other, so, you know, like this kind of random walk, there are other scenarios not to get Banaszczyk. If you get Gaussians, if you try to get this Gaussian behavior, you have to solve STP. But there are other discrepancy questions like Spencer, you don't really need to solve an STP. So for Spencer's result, using some kind of random walk like this, you can actually get very fast algorithm. Actually, there are other algorithms, not exactly based on this random walk framework, that can get nearly linear time. But that doesn't require solving STP. It requires solving some linear program, so that's very easy. But this we don't, yeah, right now it's still like conceptual, I think. Yeah. Okay, cool. Where do we improve? Yeah, you got bound from it. Yeah, and that's a surprising aspect, right? Like how you get improved bound by looking at some algorithm, but not like just thinking of it as a math question. It's quite surprising, actually. It is, yes, it is, absolutely. So where can we improve? BDG blocks large rows, generates spectrally independent updates, and this gives you a Gaussian tail for this discrepancy of small rows. Well, you can also do something better, right? It seems you can also block, say, if some rows, NT over 10 rows, have large discrepancy, you can also walk orthogonal to those rows with high discrepancy. Right? So it seems this is going to help, and this is indeed helpful in many other contexts. Like say there's this, one of the first algorithms by Lovett and Mecca for the recover Spencer's result. It uses exactly this strategy. Okay? But the trouble here is that it's not clear why it helps for to improve over Banaszczyk's result. And this is and here's an argument. Say you want to get a target discrepancy of theta times square root of k, where theta is something like log n to the 0.49. Okay? Some slight improvement. Well, how many rows will going to hit the target? It's going to be something like times e to the minus theta squared. And this, you know, it's e to the theta squared is how much the probability that every row becomes bad, and this is really expectation. I'm going to call these rows that hit target discrepancy dangerous, starting from this point. Okay, in the beginning, so, oh, by the way, how large is this number? This number is definitely much smaller than n, but it's not too much small polynomially. Say it's at least n to the 0.99, for example, right? Because theta is log n to the 0.49. So this means that in the beginning, you can afford to block all these large all these rows that get dangerous. But what happens when your dimension of freedom goes down, right? When things get colored and NT becomes much smaller than this, then you can no longer afford to block all these dangerous rows. Right? So this has been sort of the bottleneck for all previous approaches because it's unclear what to do when your NT becomes really, really small. Okay. So here's how we get around this issue. We're going to start with a thought experiment. Let's think of the rows, the discrepancy of the rows evolve independently as you evolve your coloring. Of course, this is nonsense because, right, your rows are driven by the same underlying update to your coloring. So they're very far from independent. But let's forget about this issue for now. I'll come back to it. A bigger issue, it seems that it is not helping at all by assuming the rows are updating independently. Why? I can throw you the same argument, right? Every, say, target discrepancy is something better than Banaszczyk. This many number of rows will hit the target, get dangerous. What if NT is smaller than n times e to the minus theta square? Where does the improvement even coming from? Okay, but surprisingly, you can already get an improvement here. And I'm going to show you how to get a log n to the 2/3 bound for k equal to log n. Okay, so I'm going to think of this log n to the 2/3 target as theta times square root of k, where theta is log n to the 1/6, set theta to be log n to the 1/6 in hindsight. So here, I'm going to call a row dangerous again, like, if discrepancy reaches theta times square root of k. Here's the key claim. At any time t, I claim that at most nt over 10 dangerous rows can have size larger than 10b. What is the parameter b? B is log n over theta squared, which is equal to log n to the 2/3 by our choice of theta. And in fact, we choose our theta to make this be equal to the target discrepancy. Okay. So what's the point of this key claim? Recall in the previous slide that, at certain times, there can be n times e to the minus theta square rows that get dangerous, right? That can be a much, much larger number than nt, where nt is small. But this claim is really saying, although a lot of rows can get dangerous, not many of them can have a large size. Okay, that's the key point of this claim. So I want to first finish the proof. I mean, you can sort of already see that this is very helpful because now I can block all these nt over 10 large dangerous rows. I mean, shouldn't call it large because that's, I defined it otherwise. So call these dangerous rows with size more than 10b. I can afford to block all these guys. Let me first finish the rest of the proof, and then I'll come back to prove this claim. So here's our algorithm in this ideal world. At any time t, you do these two things as before, block large rows, generate spectrally independent delta xt, but additionally, you're going to block all the dangerous rows whose sizes are more than 10b. Okay? There can be at most nt over 10 constraints like this of the third type. So we are perfectly fine. All right, here's the proof of the algorithm. So in the beginning, when a row I is large, basically we are here on this green line. The discrepancy is 0, right? We block them. Now, once your size becomes smaller than 10k, you're going to start incur discrepancy. Well, and in fact, you can start to incur a lot of discrepancy. You can touch these boundaries. These boundaries are theta times square root of k. Okay? But the point is that as long as your size is more than 10b, even if you touch the boundary, it will be blocked. So you are not going to incur any additional discrepancy. You're going to stay on the boundary. Right? So basically, whenever your size is between 10b and 10k, all those dangerous rows are going to stay at the boundary. Their discrepancy is not going to incur any further, increase any further. Okay, but once your size is smaller than 10b, well, the discrepancy can increase a bit more. But why do I care? Because they can incur at most 10b extra discrepancy, but b is our target. Okay? So we kind of get this bound up to a constant. Okay? So really, the whole point, or the main idea, is behind this key claim, right? Once you can show that not many of these dangerous rows have size more than 10b, you're all done. Let's prove this. So, okay, the proof is again the probability that each row gets dangerous is e to the minus theta squared. The key idea behind the proof is to not look at rows, but look at columns, right? Because we assume column sparsity. Fix a column J and ask how many of these ones in this column J corresponds to dangerous rows. We're going to get a bound on that. Okay, in fact, the probability, what's the probability that B of the entries in column J get dangerous? Let's do a first order computation. K over B choices of any subset of size B. among these k entries. For each fixed subset, the probability that all of them becomes bad is e to the minus theta squared times b. Okay? And this is why we choose b to be, okay, here's a large constant. Some large constant over theta squared is to make this to be 1 over poly n, so that I can do a union bound over all the columns and add the polynomial number of time steps. Okay? All right, so now what we basically showed here is that with high probability, at any time and any column has at most b dangerous entries. Now we can do our favorite averaging argument. You look at all the NT alive columns and ask, oh, how many dangerous entries are there in total in these NT columns? Well, there are at most NT times b of these red or dangerous dots, right? And then you do your averaging. There can be at most NT over 10 dangerous rows whose sizes are more than 10b. Okay? And this proves the claim. Okay, so this is why kind of random independence of the rows are going to help, and basically we crucially rely on this kind of sparsity structure that each column has k, because we are doing counting in that we're doing this kind of union bound only restrict to those k elements and do an averaging to translate back to the rows. Okay, this is the first idea, but of course the reality is that the rows are highly dependent, right? Okay, but this is a natural idea here. Just as how we can when we prove Banaszczyk's bound, we essentially say, oh, your delta xt, there's some dependence between the coordinates, and that's a problem. So we kind of make the coordinates of the coloring update to be almost pairwise independent. We can use the same kind of idea to make the rows, the discrepancy of rows, also approximately independent, right? This is some natural thing now, by adding a new set of SDP constraints. So this is what we call affine spectral independence. Recall spectral independence says the covariance of your coloring update is the most constant times the diagonal of your covariance update. And this roughly says the entries of this coloring update, delta x, is almost pairwise independent. Okay, how about let's just make this discrepancy vector update, delta dt, which is a times delta xt. How about we just make the entries of delta dt to be also almost pairwise independent, right, using some new SDP constraints. So this is what we call affine spectral independent constraints. But what it really says is that you look at the covariance of this discrepancy update vector. The covariance of delta dt is bounded by m over n times the diagonal of the covariance of delta dt. Okay. So you note that one thing before going on. First of all, this is roughly saying that delta dt has almost pairwise independent coordinates. Okay, but you see that they lose a bigger factor here of m over n, right? And this turns out to be kind of necessary because the more rows that you are trying to control here, you need to pay a price. You can't control everybody, right? This m over factor is unavoidable. But despite this kind of loss of this m over n, and that you don't really have true independence, you only get this almost pairwise independence, it turns out it suffices to give you something non-trivial. And in fact, we're going to see how to get the log n to the 3/4 bound for k equal to log n. Using a similar argument, but using approximate independence instead of full independence. Okay, and so here's the basic method. It's basically the same argument. Now you set the target discrepancy to be theta times square root of k, where theta is log n to the 1/4. Okay. The observation, here's the observation. You can discard the irrelevant rows of size smaller than log n to the 3/4. This is really what we are doing in the last step of the algorithm. When the size becomes smaller than 10b, you ignore it. This is that same thing. But now b, the threshold in which we throw away things, is log n to the 3/4. Okay. And what this gives you is that at any time, you only care about nt times log n to the 1/4 number of relevant rows. Okay. So okay, why is this? Because every row, there are nt columns, every column has log n once, right? And you only care about rows of size at least log n to the 3/4, again, by averaging. This is the number of rows that are relevant. And so basically, with this ratio you see is log n to the 1/4. So you can ensure that delta dt is log n to the 1/4 spectrally independent for the relevant rows, restricted to the relevant rows. Okay, now let's let b to be log n to the 5/4 over theta squared. Okay, earlier b is log n over theta squared, but now we are losing this additional log n to the 1/4 due to this spectral independence factor. In fact, you can prove the same kind of a very similar bound. So the probability that there are b entries that become dangerous in any column is k choose b times e to the minus theta squared b. Additionally, you lose this spectrally independent factor. Okay? And this is at most 1 over poly n by this parameter setting. So although this looks very similar, but the proof is actually a bit more complicated. Well, it's actually quite complicated. In order to prove this, you need to actually look at, you can't bound the same, like choose any fixed set and argue what happens to that set and do a union bound. You can't do things like that. In fact, we need to use a regularized version of what dangerous means and then use moment generating function to control how many entries become bad. So it's we can formalize this as a very general decoupling bound, but I won't get into the details here. Yeah, but that's essentially what you get. So after this step, you can do the same averaging argument, and this gives you a b equal to log n to the 3/4 bound for k equal to log n. Okay, so the summary of the two ideas that we've seen to improve the previous result is that if the row discrepancies evolve independently, that every column would have very few dangerous entries. Right? This means that there still can be many, many dangerous rows, but most of the rows will actually have negligible sizes, most of the dangerous rows. The second idea is you can ensure that row discrepancies are approximately independent by adding a set of new SDP constraints. And this weak independence is already enough to give you some non-trivial bound. And this, this framework is very flexible, and there you can get further extensions. And let me briefly discuss these. The first is how you get a Koml bound of log into the 1/4. Recall our basic method shows that you can get a square root of k times log into the 1/4 for all k. We only show this for k equal to log n, but this is what you can get more generally. So you can view a Koml instance as a Beck-Fiala instances at multiple different scales, right, depending on how large the entries are. You want to do a dyadic scale and break your Koml instance as sort of many different scales, but how many scales do you need? Naively, if you do it naively, you care about the entries of the Beck-Fiala problem between 1 over n and 1. So naively, if you do a dyadic scale, that will give you log n scales, but this is too much. In fact, there are effectively only log n scales, constant times log n scales, and this is because you can actually ignore all the entries of size smaller than 1 over polylog. Because, in fact, when k is larger than log n cubed, if you do the basic method more carefully, you don't just get this square root of k times log n to the 1/4, you actually get square root of k times log n. So to just quickly mention, because someone asked this question the other day when I gave the talk somewhere else, they asked, oh, why do you get this improvement? Roughly speaking, recall that when k equals log n, we're going to ignore rows of size b, where b is that target, right? Suppose you are shooting for a larger k, you're shooting for a discrepancy of, say, square root of k times log n. If you do that, you're essentially throwing away rows of size square root of k times log n, which is quite wasteful. That's pretty small. In fact, you can throw away rows of size k over log n by applying Banaszczyk after that step, instead of just simply bounding their additional discrepancy by the sizes. So you use Banaszczyk's square root of the remainder size times square root of log n. So that will allow you, in short, that will allow you to throw away rows of much bigger sizes, and that gives the improvement here. Yeah, I can go into details afterwards, but I will mention some other things. One thing here is that you need some care to handle all the scales simultaneously, because all the scales share the same coloring. Okay? But you can do this by only losing this log n factor. All right. Some other extensions, how do you get the stronger Beck-Fiala bound? Well, recall that in this basic method, what we essentially say is that restricted to the dangerous rows, every column has sparsity b, which is much, much smaller than k. Okay? And then we're going to use the statement that how many of the, right, we basically say in every column there are at most b dangerous entries. We use this to translate back to how many dangerous rows have size larger than 10b, and say we can block all these, all the relevant dangerous rows. This is our argument. In order for this argument to work, this column sparsity b of dangerous rows has to be much, much smaller than k. It, in fact, has to be our target discrepancy bound. Okay? But one thing is that we don't have to rush to block these relevant dangerous rows. In fact, here's a more useful view, a more generic view. We can view these dangerous rows as another Beck-Fiala instance with sparsity b. And as long as the sparsity b is smaller than this k by a constant factor, like say k over 100, we're already making very good progress. And what we can simply do is to run a recursive algorithm on top of these dangerous rows. So this gives us this multi-layer kind of algorithm. So in the beginning, all the rows start at the ground level. And as I run so I'm going to run all these algorithms in parallel. Okay? In the beginning, everyone is in the ground level. Okay? All these other algorithms are not doing anything. But as I run this algorithm and generate colorings, and some rows get dangerous, they will get upgraded to level 1. And that level 1 algorithm is in charge of handling those dangerous rows. And as you keep running, so some of the level 1 algorithms is going to get dangerous again at level 1, and it's going to move upwards. The crucial point here is that as long as whenever you move up a level, the sparsity goes down by a constant factor. You have this geometric decay of how much discrepancy you incur at each different level, right? And basically, you can pretend that all you need to bound is what is the discrepancy incurred in the ground level by making the sparsity b to be k over 100 instead of like something like from log n to log n to the 3/4. So that's that basically says you don't have to make sparsities go down so low in one step. You can take gradual steps. Okay, and this if you do this more carefully, this gives you the square root of k Beck-Fiala bound for k being at least log n squared, and for k to log n equal to log n, this will recover the ideal world algorithm, log n to 2/3.
So if you implemented this, would you just always be working on the highest level that you are currently at until it was resolved and sort of go back down and then continue working at the next highest?
So you mean with this kind of, you have to do it I think you have to do everything in parallel. So what happens is that when you really think about algorithm, that's basically about writing out the semi-definite program. So you're going to write that semi-definite program with one set of this. It never comes back down. Yes. Yeah. That's good point. That's very, very important. Yeah. If it goes back down, the analysis would actually not work. So it has to be like, when it goes to the very top level here and still get dangerous, that's when it's going to get blocked. But very, very few elements, very, very few rows are actually going to become dangerous at the top level. Yes. Yeah, and by handling all these rows simultaneously, handling all these levels simultaneously, I mean that you write the SDP, but you generate this kind of affine spectral independence constraints for every level. You put all of them in your same SDP. I'm in trouble with this. Okay. Gotcha. Yeah, no, that's okay. I feel as long as whenever I lean like backward, this will going to fall down because this is a little bit too short. Yeah, that's fine. Yeah, but basically that's what I meant. And for the Koml problem, you also need a similar thing. So is it am I out of time?
5 minutes, let's say.
Okay, good. So I will be wrapping up with maybe another 1 or 2 slides. So a natural question is how you get further progress for k being smaller than log n squared. The current bound is something like square root of k plus square root of log n, and this square root of log n actually leads to the square root of log n to the 1/4 bottleneck for the Koml problem. So the problem here, the reason why we are stuck at this log n square root of log n is because we need concentration. We want few dangerous entries to be in every column, and the reason is that we don't have control on which NT columns are remaining at time t. Right? If you have some columns with more dangerous entries, the adversary could just keep those columns. We don't have any control, and the averaging argument would fail. So and it turns out even some mild non-adversarial guarantee on which columns survive, that might be very helpful already, but we don't know how to get that guarantee so far. Okay, finally, open problems. So the first, of course, is how you get resolve the Beck-Fiala conjecture for k smaller than log n squared. One thing I didn't really mention earlier is that actually if A has no large row to begin with and you do a uniformly random coloring, you don't just get square root of k times square root of log n as in Banaszczyk. You get square root of k times square root of log k by applying the Lovász local lemma and show that you can use algorithmic version of this lemma to show that some you efficiently compute a coloring with this bound. And when k is small, this is square root of k times square root of log n. And this gives some hope of getting the square root of k times square root of log n for k small. Because Beck-Fiala intuitions that you can pretend large rows don't exist, right? But the issue here is that right now we don't know how to combine the argument for the Lovász local lemma with this kind of walk orthogonal ideas that I discussed in this talk. These two are so far very different proofs. If you can have some way to combine them, with very interesting, it might even directly lead to a polylog-log bound for Komlos. Okay. So another problem is a different set of problems called prefix discrepancy problems. So it's basically in Komlos, instead of looking at the discrepancy of all the vectors, you might want to look at discrepancy of all the prefixes of the vectors, right? And Banaszczyk has a follow-up paper which gets you square root of log n even for all the prefixes. But here, the algorithmic aspect is a bit more tricky. We only know how to get log n algorithmically. And existentially, you can sort of believe this is a much harder objective, and maybe Komlos would not be true for prefixes, but we don't know how to prove that yet. And even for the two sparse version, this question is widely open. It's still the same status as the general problem. And two sparse is motivated by some application to scheduling by recent work of Bansel, Rohleder, and Svensson. There are other many related questions that has a prefix flavor. Won't dive into this, but prefix is a very useful structure in general, and we still lack some basic understanding about them. That's everything I want to talk about. Thank you for your attention.
Thanks. For those online, feel free to unmute yourself and ask questions or put them in the chat. I'll stop recording now.